Here the scanning convolutional neural network models. I'm Phúc, I'm the master student of CMA. Today I present about this topic. And here our object of automatic neural network architecture. And the model can be either designed manually or automatically. And his inception ResNet is the model designed by hand, and the natural automatic neural network architecture design automatically. Here's the experiences with two kind of network, the one with automatic methods and another with handcraft, decided by hand. Previous automatic methods do not reach the higher performance than the handcraft model, so we need a better algorithm in the automatic neural network architecture. And the second motivation is that when we, from the automatic architecture, we have the baseline models and we want to increase the accuracy more, but we can increase the size model. However, we have problem with the memory because we are limited memory. As you can see here, two kind of network, the REST network 50 layers and the REST network 152 layers. As we increase the number of parameters, the number of accuracy also increase. However, it's hard for us to use the model with very heavy inside. The model is very big because some model need to be run inside the mobile device or embedded system where the hardware memory is limited. And here's the search page. Here's the search strategy. From the search page, they use the algorithm to pick up the architecture search from the search page, and then based on the estimation strategy or the metric like accuracy, we pick up the accuracy, the architecture from the search page and evaluate it to choose the best models, the best performance. So what is the search page? The search page is the space contains a lot of architectures where we can pick up the suitable architecture. As you can see, we can pick up the suitable architecture with high performance. And then you can see the mission of search space is that we look for the structure of this inception like network like this one. And as you can see, we have a lot of hidden layers, a hidden stage. We have two hidden stage 0 and 1, and from that we put into the average pooling and mass pooling, and mass pooling to create the hidden stage 2. And from the hidden stage 0, 1, 2, we can either from the hidden concatenated from the hidden stage 3. And as you can see, there is another operation here. It's called the separate convolution layer. In this structure, we have totally 5 pairs here, and the last 2 hidden state is undue, and it's just concatenated from the hidden state 7. And here's the random search. In the random search, the number of points in the 2D search space does not likely equal distribute. However, in the search phase, likely equal distribute. And the random search in the search strategy, it means that all the architecture is equally independently designed, and this means that equal chance to be picked up. And here's reinforcement learning methods is one of the strategies of previous work. As you can see, we have the controlling that's built on the RNN reinforcement learning, and then we train the children network with the architecture to be convenient to get the controller. We generate different kind of models. From that, we train the children architecture and to convent to get the very high validation accuracy. And then they fit up the validation accuracy. That's the accuracy evaluated based on the validation set. And to check what the validation set, because the data distancing by the models, so if it into the controller will pay on the validation accuracy to evaluate to generate a new architecture and fit into to generate a new architecture. With higher performance. And as you can see, but however we want to have the higher performance, so we should improve the evolution algorithm within the Asian evolution to make it better performance, to have its better performance. And here is the Asian evolution with genotyping these and favors young. It means that it's remove the oldest architecture from the population. At first you can see that is initialize the count 1, and then it's from the population. The population is that the numbers individuals in the population. And the reason why we do this is because we want to every architecture had likely equal chance to be picked up in the search space, and then we add in the first in and first out query. As you can see that and later we need to sample from the case sample from the population. And because the reason why we need to sample one more time uniformly, because we want that weaker architecture have equal chance to be picked up, because in later it can perform better. So we select the fit from the case sample and assign them as a parent, and we do some kind of mutation. It means that some kind of transformation is equal the mutation, and add them the children and train evaluate the children. And here the mutation, as you can see, there are two type mutation. The first one is hidden state mutation, and this one of 5 pair on the structure that I showed previous slide, and we pick up randomly this for one of these pair, one of these 5 pair. One is this 5 pair. One of these 5 pairs is called 5 pairs, and then we choose randomly one of 2 elements, the separate convolution and the average pooling, and then one of the hidden state from the separate convolution layer. We the one element with only have one hidden state tree, like this one we change with another hidden state within hidden state 4, and we do the same things with the operation mutation. The different thing is that we change the operation, not the hidden layer, hidden state. So there is many kind of operation that we can choose on either average pooling, mass pooling, or separate convolution, and we choose randomly. And mutation like exploration, and parents select parent like exploitation. And as you can see, the children were trained on and to the population It means that we favor the young, and it means we remove the one individual from the end of the queue. It means that we remove the oldest. We increase the number of counted by one until reach the default cycle that we use a default cycle, and the cycle is need to be smaller than the population size. So one more thing about the Asian evolution. So why we call it the Asian evolution, because non-Asian nation evolution is previous work. We discard the world model, and Asian evolution is mean we kill it the oldest model. The reason why we have the advanced method, which is called Asian evolution, because we give the chance for the weaker architecture. Maybe in later they have performance better. On the right side, you can see that there is a mean time accuracy performance, and this was evaluated about 200,000 models compared Asian evolution and non-Asian evolution at scale. And as you can see, we increase the number of P called the population individual in the population, and the sample is called the number of samples in the number of samples. And if we increase this P and X, we increase P and S. However, the Asian evolution is performing better, even that they have smaller number of population and the sample size. And all of this model is just the baseline. We need to be scaled up in order to have better performance. And now we move on to performance strategy. Performance strategies is all the that it's been that we train our children network architecture from the produced by the by the shared strategy, and the matter accuracy on the validation set means that the text set we use for evaluator accuracy. And here on the right side of the screen, you can see that we have the evolution algorithm. The experiences of different kind of evolution algorithm, reinforcement learning, and random search. And as you can see, we increase the number of time simulation. We increase the number of experiment time hours, and then the evolution must perform better, and is really high performance in the early stage, so we can use this criteria to stop early, and later experience, and the accuracy of evolution still perform much better than the informant learning on the random search. On the right side, you can see that we compare different type models, the ResNet with 101 layers, and the automatic methods, and we have the evolution, the model produced by the evolution algorithm. Even though the number of parameters of the evolution produced by the model produced by the Asian evolution is much smaller, they still perform better. And from the neural network architecture, we have a good baseline network with the reasonable, with the better accuracy, but we want to improve it further by scaling those network higher. Previous work, there are three types of the scaling the convolutional neural network. The first one is using the with scaling. As you can see, it's the baseline architecture, and here's the number of channels in each layer in this stage, and here's the resolution. And we want to scale the width of each channel in each state, and if we scale it up, the width, and it means we increase the number of slots of the network. And as you can see is that when we scale the different kind of width, the accuracy increase. However, it was saturated. So the reason why it is the network is hard for the network to recognize the higher level architecture is we should only increase the number, the width, which is the number of channels in the convolution layer. And another method we increase the depth. It means that the number of layers in each stage, the depth layer increase, so the network is likely to recognize higher resolution features. And if we increase the depth, it means that we increase the number of slots in the neutral aggregate search. And however, it was saturated if we have too much. The floating means that the number of operations we have is equivalent to the parameters of our models. With we go deeper, we have the problem with Van gradient descent, and it's really hard to update the parameters the way it in the early layers. So it was saturated also. And another thing is that we increase the resolution of image, and it means that we have more detail in the input image. The model is performing better because they have more detail to recognize. However, and this means that we need to increase the parameter, the convolution layer in the input layer, and it's increase the number of slots also. However, you can see that we increase the input of the image, the resolution image, and the accuracy increase. However, this was saturated. Like previous two methods. This is because the network do not have enough width and depth to recognize the grain or the depth features. What is proposed compound scaling? So what is proposed compound scaling? We have higher accuracies. Previous work we have the higher accuracy scaling any dimension. We scan the depth, width, and resolution. The accuracy can quickly diminish. The reason why it's quickly diminished in previous observation. However, another observation is that we need to balance all dimensions, because for higher resolution image we need a higher layer, more layer to observe more higher level features, and more channels to observe more detailed fine grained features. And another thing on the right side is the experiences with the efficiency net P1 with different methods. The efficiency net was produced by scaling. This is a baseline network for we use for scaling. If we scale independently, it means that the accuracy very much lower than we use the proposed compound scaling. So what is proposed compound scaling mean? Proposed compound scaling means uniform scale of the network with depth and resolution. As you can see, here is the formula of this method. The V is called user-defined input. User-defined variables to show how many resources we can have. The depth means the alpha power fees mean how many depth we can expand, and the width that how many the beta power feed how many width we can also expand. The resolution is mean that how many resolution we can expand. Subject to constraint alpha, the beta power 2, and the gamma power 2 is approximate 2. The more approximate we want to, if we use 2 with depth resolution, we want to expand all of this equation. We use G equation to explain with the depth resolution, and the result is that the number of floats will increase more than 2 power 3, and so we need to have the constraint in order to the number of floats is not increase over 2 power 3. The reason why because we want more accuracy, and of course we want to scale up, not scale down, so the alpha beta gamma needs to be greater than 1. However, in special case like embedded system, we need scale out in order to have some kind of architecture run in the embedded system, for example. And the depth, for example, we want to increase the depth by 2 times, and it means that we increase the number of floats in our model 2 times. However, the width and the resolution with the width and the resolution, it means that we 4 times increase the number of floats of our model. And here step by step we use. First we need to fit the phi and do more research and find the best value of gamma, beta and alpha, and later we fit all of the gamma, beta, alpha, gamma, beta as a constant and scale up the baseline network. And it's the results measuring. As you can see that here is the baseline network, ResNet with 50 layers, and then we scale independently with the depth and the resolution. And here's the height accuracy before it's saturated. And as you can see, it cannot go further if we scale only this or 2 dimensions independently. So we need to use the compound scaling. By using the compound scaling, as you can see that the accuracy of the ResNet increase higher than we scale independently, but the number of floats is just not much higher than scaling by the independently by using the scaling the dimension by the depth, by the width and the resolution. And in summary, in these 2 papers, thus we get the knowledge about how we can have a good performance models. At first, we use the Asian evolution with variant tournament selection. It means that from the children architecture from the population until we train the children. This called the variant tournament selection, and genotyping these and favor the young. It means that we try to keep the population, the architect in the population at the finite time, and we remove the oldest population from the oldest architecture from the population. To further improve performance, we have another method which is called the pole compound scaling. We uniform scaling all dimensions, the width, the depth, and the resolution from the baseline network that we have by using the Asian evolution. And here's the bibliography. You see, thank you very much for everyone to listening. If you have further, and thank you for my supervisor who support me writing the report as well as the presentation. If you have any further question, please don't hesitate to ask me.